gravitational potential energy. So previously, we talked about the gravitational potential energy, mgh, which is related to the weight, mg. So if this is a special case, this gravitational potential energy is also a special case, mgh or mgy. Okay, it's derived from the spatial expression of the gravitational force. Now we have a more general expression for the gravitational force. So that means if the object is not just located near the Earth's surface, we have to introduce a new equation to calculate the gravitational potential energy. The new equation is this one. Okay, so this is a general equation for the gravitational potential energy. This is a special case when you're talking about some motion close to the Earth's surface. So before we look at this expression in details, let's talk about this issue. When should you use this equation, and when should you use this equation? So for this one, you are going to talk about some motion near the Earth's surface. So the height change, okay, for the motion should be small compared with the Earth's radius. Okay, no matter if, like say, the height change is 1 meter, 10 meter, or even 100 meter, okay, they are okay. They are really small compared to Earth's radius, because the Earth's radius, let's see, what's the radius of Earth? Okay, it's 6.37 times 10 to the power of 6. Okay, so it's this one. That's the Earth's radius. So if your height change is much smaller than that, you can always use the spatial case. And you can see most of the motion we are considering, even say I'm dropping the ball from the highest building in the Earth. Okay, I don't remember what is the highest building. I think it's maybe something like 500 meters. You can see 500 meters is still much smaller than this number, right? It's even less than 1%, less than much smaller than 1%. Okay, 500. This is about more than. Okay, so it's maybe 0.01%, right? The distance change compared with the radius. So it's very small. So you can still use that one. Okay, but if you are talking about the motion of like satellites, these things, then the height change, if you launch a satellite from the Earth's surface to the orbit of the satellite, the height change will be very large and comparable with the Earth's surface radius. So for the motion of the satellite, you have to use this more general stuff. Okay? Any question here? Okay, now let's see how can we get this equation. Okay, in fact, we do have the definition of the gravitational potential for any arbitrary force. Do you remember that? We define the potential energy change, delta U, as the negative work done by the corresponding force here. Okay, so if we're talking about the gravitational potential energy. That's the negative value for the work done by the gravitational force, right? That's a definition for the potential energy. So now we can try to use this definition to do the calculation. So delta U will be the final U subtract the initial U, okay? Of course, the final U is the value of the final U depends on the zero reference point you are going to set. Here, negative, the work done by any force in general is defined as the integral of the force, okay, with respect to the displacement. In this case, displacement is characterized by the radius here. Okay, it's a vector definition, so it's dot product. In fact, it's this. Okay. Now we can try to simplify this dot product. We can think about this because when you define, okay, let's see, if this is say the Earth's surface, okay, if we try to calculate delta U, like from point A, like here, to point B to here, okay, the work itself can be done by any path, like this path, or this path, right? But it's a potential energy. So that means the force is conservative force. The work done by the conservative force is independent with the path. Okay? That's the definition. So use this fact, we can choose the most easy path to do the calculation. And of course, the most easy path in this case is from the straight line from A to B. So we are going to calculate the work from here to here. And the final result is independent with the choice, because from along any path you are going to get the same answer, right? Okay? So now, then we are trying to evaluate the integral from point A to point B. Okay. So we can simplify this. Now, in this case, for this one, in general, the force and the direction of the R can be in any two different directions. But if we choose to calculate it along this path, so the gravitational force, if you have particles, think about particles, move from here to here. So the direction of the R is in this direction, right? And the direction of the force is in this direction. It's always so, right? From here to here. They are always opposite to each other. In this case, FdR, if you dot, will become negative FdR. Right? Any question here? If they are opposite with each other. So the angle between them, because this one is Fr cosine theta. Right? FdR. Okay? And cosine theta is the angle, so it should be cosine opposite with each other, so it should be cosine 180 degree, which is negative, so it will give you negative FdR. So, okay, U minus U naught equals to negative FdR. And U minus U naught here, negative makes positive FdR. Okay? So now I'm changing this vector equation to a scalar equation. Now it's a scalar equation. It's in one dimension. You just integrate the force along R direction. Also, during this manipulation, I also killed the negative side by another negative side. Okay? Do you have any question so far? Now, this integral should be easy. I'm going to integrate it from our initial stage, so R naught, if the radius for the initial state is called r naught, and r is the radius for our final point, I'm going to integrate from r naught to r. And so u minus u naught equals to r naught to r. This is the gravitational force Fg, okay? So it's given by this equation. G capital M small m over r squared dr. Okay. And then u minus u naught equals to G capital M small m r naught to r 1 over r squared dr. I can factor out this constant, okay? This masses and gravitational constant. And this is integral, you know how to evaluate it, right? If you want to integrate 1 over r squared, what are you going to get? Remember? Negative 1 over r, right? Okay? So u minus u naught equals to negative 1 over r. This integral should be evaluated, this result should be evaluated from the lower limit to the upper limit. Okay? Any question here?
How'd you get the negative?
Okay. I think the general equation is that if you have x to the power of n, right? If you want to integrate it, it should be n minus 1. Okay. Okay, and what's the general? X times. Is that correct?
Yeah.
Minus 1, right?
N times x.
Oh, x, yes. Okay. Let's see first. No. Okay.
Isn't it divided by n?
Oh, divided by n?
Yeah.
And minus 1. Plus 1? Okay, it's hardly difficult. Okay, let me do it this way. I cannot remember it either. Okay, I haven't do this long time ago. Let me do this. I remember the derivative. This one, if you take the derivative, it should be n x n minus 1. That should be no problem. That's definitely correct. So if I want to invert it, so that means x n minus 1, go back, should give you integrate it n over n x to the n, right? And if it's x, so x to the power of n, if you integrate it, so if you add 1 here, so n plus 1 multiplied x, n plus 1. Okay, so should be this, right? Okay, so this is not correct. So you see, in fact, I cannot memorize many equations. I can only memorize a few, but if you understand it, you should be able to get it correct. So if you use this one, we have 1 over r squared. In fact, it's r to the power of negative 2, right? And if you get it, then here x negative 2 plus 1. Here you get negative 2 plus 1. So it gives you negative x to the power of negative 1, which is negative 1 over r. Here we have r. Okay? Integral here. That's my way to memorize it if I have to. Okay? I hope it helps you to get the right equation. Or probably you can just directly memorize it, because that's a very common integral. So if you want to integrate 1 over x squared, you can memorize this. It should give you 1 over x, negative 1 over x. Okay, then if you substitute the number, it will give u minus u naught equals to negative G capital M small m 1 over R minus, and you have one more minus here, so it's plus G capital M small m 1 over R naught. Remember, you have one minus side from the integral evaluation here, you have one more minus side here. So that's the equation you are going to get from the integral. Any question here? Now, you still need to fix the reference point. This one just says that if you want to get some value for the gravitational potential energy U, it depends on where you are going to choose as your R naught and what you are going to put for the reference. Of course, you are going to put reference point for 0. So, but the question is that you are going to put somewhere U naught equals to 0. But what is the best choice? When R naught equals to what, you are going to put U naught equals to 0. Can look at this equation to make the best choice. If that's the equation. What value you are going to choose for R naught to set U naught equals to 0 will give you the simplistic equation. Infinity. Can you see that? Can you help me to explain why I want to put R naught equals to infinity, the U naught equals to
1
0.
over infinity 0.
Yeah, because I want to get rid of this term. So when R naught equals to infinity, 1 over R naught equals to 0. So both of them will go away. So finally, this is 0, this is 0. So you get U equals to negative G capital M.
Also infinity center on there.
So that's where how we get that expression. So, okay, so what do you know that, what you have to know for this is that if you say the gravitational potential energy equals to negative G capital M small m over R, that means with this expression you assume an infinity distance R equals to infinity. The gravitational potential energy is 0. Okay? And by the way, you can see that for this expression, at any point, the gravitational potential energy is a negative value, right? No matter which R you are going to take, it's always negative. That's because we choose the infinite and infinite, the value is 0. So any place, any distance less than the infinite place, which means any place should give you the negative or smaller gravitational potential energy. Okay, because at the infinite you have the largest one. Okay, so don't get don't feel strange if you always get the negative value for the potential energy in this expression. Question?
Can you explain how you went from infinity and got rid of U naught?
Okay, you want to set U naught equals to 0 for that point. Remember, when we talk about gravitational potential energy, the value depends on where you are going to set it at 0. Like if you set the ground, even for this one, at 0, or you can set it at the building, top of the building equals to 0. Okay. So in this case, you are not going to choose. We always set U naught, the gravitational potential energy equals to 0 when R naught equals to infinite. Okay. This one is you choose, you set it as 0. Okay? In fact, there is nothing wrong. You set it as any other number. You can set it to 10 joule, 100 joule. It wouldn't change any calculation. Okay, because that's just some reference point. During the calculation, it will be cancelled anyway.
For when we're calculating the potential energy, since we're going to get it to come out as negative? Do you want us to take the absolute value of it?
No,
so we have
don't
a
take
positive
absolute value for the potential energy. Okay, just leave it as negative. So this is something now you have. Previously, when you talk about the scalar quantity, we always make some positive number for it. But in this case, keep the negative side here. Okay, it indicates that it's less than some value. Okay, that's a convention. But this is totally comes from this fact. Okay, now, of course, this kind of potential energy, it's defined the potential energy for a pair of objects. Okay, so like if you have Earth here, you have another object moving from here to here. So this is our object 1, this is our object 2. Okay, so it's the gravitational potential energy between the two objects. If you have several planets or satellite like this, you can have like say Sun here, Earth here, Moon here. Okay, if you try to calculate the gravitational potential energy for the whole system, you need to consider all the possible pair of masses. How many pairs do you have here?
6, 9.
3 objects, how many pairs?
9.
Only 3 pairs, right? Pair 1 and 2, pair 2 and 3, and pair 3 and 1. That's a gravitational potential energy. You have 1 potential energy for each pair, not 2, okay? And how about if you have 4 objects, like if you add 1 more, like say another satellite, 4. How many pairs do you have? 6. Okay, if you have 4 objects, 1 pair, 1, 2, 3, 4, 5, 6. Okay, so if you try to calculate the total gravitational potential energy for this system, you are going to have 6 terms. Okay, similarly, if you have 5, there are more pairs. Okay, so that's the gravitational potential energy. Now,